Hello everyone, my name is Ntormousi, and today I'm going to talk to you about some recent work on global MHD galaxy simulations with a particular emphasis on the role of feedback on the morphology of the magnetic field and on the emergence of a nuclear dynamo in these models. So I'm going to start with a very short introduction telling you something you already know, that galaxies are magnetized. Present-day galaxies, we know that they possess a coherent magnetic field with a typical strength of a few microgauss. But we also know that at redshifts 1 and 2, galaxies already probably had these strengths, these magnetic field strengths in their ISM. So for most of their lives, well, for a large portion of their lives, galaxies have an important degree of magneticization as well. The other element that I wanted to highlight is that recently we have gained access to the magnetic field of other galaxies as traced by different phases of the ISM. Here I'm showing you this impressive image from a recent paper by Alejandro Serrano, where on the left, you can see in this wavy pattern the magnetic field as traced by dust polarization, and on the right, the magnetic field from an older work as traced by radio polarization. So this complexity that we are now starting to understand is also an important ingredient in the ISM dynamics. The dynamical role of the galactic magnetic field has been known for long time, has been analyzed in theoretical and numerical work. The galactic magnetic field provides a source of pressure. It also controls the propagation of cosmic rays in the ISM. It affects the behavior of turbulence. And through the Parker instability, it can also decide where molecular clouds form. All of this points to the need for a global and self-consistent picture of the galactic magnetic field if we want to understand the dynamics of the interstellar medium. And this is what I'm going to present to you today. Two families of models with a similar setup, all done with a Ramses code. Ramses can handle collisionless components and a grid with MHD variables on an adaptive grid. So here we have set up dark matter halo with a stellar disk performed with a collisionless solver, the solver treating the collisionless particles, and a gaseous disk making up maximum 1% of the total mass with a toroidal or colloidal magnetic field treated by the AMR. The first type of model treats the AMR almost like a nested grid. So we have a coarse resolution of 256 cubed in a 60 kiloparsec box, and the entire disk is simulated with an effective resolution of 1024 cubed. And this family of models contains 6 simulations that I'm going to very briefly introduce. FB stands for feedback, so there are 3 with feedback and 3 without. B is the plasma beta strength at the center of the galaxy, and the strength is exponentially dropping with radius and height. T and P stand for toroidal and colloidal initial morphology. These models cannot be evolved for a very long time because the high resolution makes the time steps tiny. But already after only 15 megayears, we can appreciate very strong differences in the morphology of the magnetic field. Here I'm showing you volume rendering of the density, the gas density, with arrows showing the magnetic field. On the left column, we have 2 models with feedback, and on the right, 2 models without feedback. The top 2 galaxies initially had a colloidal magnetic field, and the bottom 2 a toroidal magnetic field. And it's clear that the galaxies on the left column have a more randomized field than those on the right column. This can be more easily appreciated in power spectra. Here I'm showing you two power spectra of the models in the magnetic field on the left and the kinetic energy on the right. The green, blue, and cyan are the models without feedback, and the red, purple, brown, and pink colors are models with feedback. The kinetic energy power spectra, it's clear that these split into two families, feedback, no feedback, with the feedback showing power up to very large scales. On the left, the picture is more complex, but what I want you to keep from this is that on small scales, all the models show a random magnetic field, which probably points to some inherent stability of the field, randomizing it on the scales. Now, the second type of model abandons this very high resolution in the disk and goes for a more traditional AMR approach, which means that we have same 5 levels of AMR, but now they are following the density distribution and the star formation regions. The reference model in this will be model M with an initially toroidal magnetic field and supernova feedback. And I will be mostly comparing it with model M no feedback, which is its counterpart without feedback. So here's the time evolution of these models. We were able to run them up to 2 gigayears. On the left is model M without feedback, and on the right is model M. You can see the volume rendering with the magnetic field lines. They are also very randomized very early on. But what is interesting here is that both models M and model M no feedback show an amplification of the initial magnetic energy by a factor of 100 over half a gigayear. Interestingly, this is the same timescale for the formation of the central bar, the galaxy. Whether or not there is a connection between the two is something that we cannot establish with this model alone. But the question arose then when we discovered this, can there be a mean field dynamo in action here, even though we didn't prescribe it? And I'm going to briefly show you some evidence showing that it may very well be. Here on the top, I'm plotting some magnetic field lines 1.5 megayears apart. The green one, if you follow it closely, seems to be twisting and being wounded up in the center of the galaxy. And at the bottom, similar picture, where again, the green line shows you the magnetic field loops being twisted in opposite directions, up and down, above and below this, which is a very nice indication of the alpha-omega mechanism at work. Now here I'm showing you the mean component of the magnetic field. So another nice probe of the dynamo. We want to see the morphology of the field on a large scale, of the mean field, say. Here on the top, I have convolved the magnetic field distribution with an 8-cell kernel, a median kernel. So what is kept by this kernel is the mean field that I'm contouring on the XZ plane. And the bottom is the same image for models M and model M no feedback, but with a 16-cell kernel. These kernels mostly correspond to the size of super bubbles exploding in the disk and the scale height of the disk. So what you see here is a mostly quadrupolar magnetic field topology in the disk. It's very reminiscent from the predictions of analytical models like the one I'm showing you here from the work of Sticks in 1975. Well, this brings me to my summary. I have shown you that with global MHD galaxy simulations, we can already probe many characteristics of the evolution of the magnetic field. The open questions I would like to leave for discussion relates to the dynamo, nuclear dynamo that is present in these simulations. First, that the timescale coincides with the formation of the bar. So I wonder, is this a persistent characteristic of isolated galaxy models, and what parameter space we would need to cover in order to understand this phenomenon? The other has to do with amplification factor. Here, we only get an amplification of the magnetic field energy by a factor of 100, which is still very much below equipartition. How do we get to the equipartition values, and what is the role of small-scale turbulence in this process is another direction that we should explore with future models. And here we'll stop, and thank you very much for your attention.